Resistivity. Here we have a model of current passing through a wire. A small section of the wire has been enlarged, allowing us to see the electrons moving from the negative to the positive side. As they go, they collide with the positive ions. The resistance is caused by these collisions between the electrons and the positive ions. Some materials are easier for the charges to pass through than others. The level of resistance to current of a particular material is its resistivity. This model represents a different material with a different arrangement of the positive ions, and this material produces far fewer collisions, so it has a lower resistivity. It's much easier for the electrons to pass through. Resistivity is a property of a material, whereas resistance is a property of an object. With a longer piece of wire, as we have here, the number of collisions will increase. And if we double the length of wire, we will get double the number of collisions, and therefore double the resistance. This tells us that resistance is directly proportional to length. Here we have a thicker piece of wire, and increasing the cross-sectional area increases the number of routes available to the charges, and therefore reduces the resistance. We can show that doubling the area will halve the resistance, and so we can say that the resistance is inversely proportional to the cross-sectional area of the wire. Combining those findings gives us this equation. R is equal to rho L over A, where R is the resistance of the object in ohms, L is the length of the object in meters, A is the cross-sectional area of the object in square meters, and rho is the resistivity. To find the units of resistivity, I'll rearrange the equation to give rho is equal to resistance multiplied by area divided by length. Then in terms of units, we get resistance in ohms, area in square meters, and length in meters. The meters on the bottom cancel with one of the meters on the top to give the units of resistivity of ohm meters. Copper has a very low resistivity of 1.7 times 10 to the minus 8 ohm meters. This means copper is a very good conductor. Polythene, an insulator, has a very high resistivity of around 10 to the 16 ohm meters. This shows a huge range from a very good conductor to a very good insulator. Let's just look at this problem. A 40 centimeter length of wire with a diameter of 0.5 millimeters passes a current of 0.2 amps when connected to a 1.5 volt cell. Calculate the resistivity of the metal. Well, we've got quite a few mixed up units here. We've got the length in centimeters, which I'm going to convert to SI units of meters, and quote here my length as 0.40 meters. I've been given the diameter of the wire in millimeters, and I want the area. Well, I know that the area of a circle is pi r squared, and that is also equal to pi d squared over 4, with d being their diameter. So I can write the area as pi d squared over 4, which is pi times the diameter of 0.5 times 10 to the minus 3, because it's millimeters, squared, divided by 4, giving an area of 1.96 times 10 to the minus 7 square meters. If you're more comfortable in first finding the radius by halving the diameter, and then using area as equal to pi r squared, feel free. It's just one extra calculation to do. We're not given the resistance, but we know that resistance is equal to potential difference over current, which in this case is a potential difference of 1.5 volts going here over a current of 0.2 amps which goes here. That gives us a resistance of 7.5 ohms. Now we're asked to find resistivity, so we're ready to write our equation of resistivity is equal to resistance multiplied by area divided by length. And we found the resistance of 7.5 ohms, the area of 1.96 times 10 to the minus 7 square meters, and the length of 0.4 meters, giving a resistivity for this material of 3.68 times 10 to the minus 6 ohm meters. Resistivity and temperature. In a metal, an increase in temperature has little effect on the dimensions or on the number of charge carriers or free electrons that are available. There is, however, increased kinetic energy of the ions within the metal, leading to more vigorous vibrations and so more collisions between the ions and the conduction electrons. This leads to an increase in resistivity as temperature increases. In a thermistor, an NTC or negative temperature coefficient thermistor, a rise in temperature releases more charge carriers, and this leads to a reduction in the resistivity.